Welcome back, everyone. Our final speaker of today is Professor Sorin Dumitrescu. He'll speak on curves in compact quotients of SL2C.
Thank you. I'd like to thank the organizer for the nice conference. I was in ICTS just before the pandemic. It was in February 2020. And at some point during the lockdown, I was thinking maybe I will be able to come again in ICTS. And I'm very happy to be here again after this pandemic. So I will present you results which were proved during the lockdown with my colleagues and friends, Indranil Biswas, Lynn Heller, and Sebastian Heller. It's about what could be found inside quotients of SL2 of C by uniform lattices. So those quotients I was talking about are what we call parallelizable complex manifolds. So we have seen some nice example of abelian varieties, which are parallelizable manifolds. We have also compact complex torus, which are quotient of Cn by a lattice. And some other examples are quotient of any complex Lie group by a uniform lattice in it. All those examples have holomorphic tangent bundle, which is holomorphically trivial. Now, the theorem stated here, which is not hard to prove, is the fact that conversely, if you have some compact complex manifold such that the holomorphic tangent bundle is holomorphically trivial, it should be a quotient of a complex Lie group by a uniform lattice. Moreover, it's also easy to see that the only examples which are Kähler manifolds are those compact complex tori. All the other admit holomorphic one forms, which are translation invariant, but not closed. So the property for a holomorphic one form to be closed on a Kähler manifold, it's not true on quotients of complex Lie groups, which are not abelian. Now, my example today would be a non-Kähler manifold, which is a quotient of SL2 of C. And those particular examples of parallelizable manifolds are very closely related to hyperbolic 3 geometry. This comes, of course, from the fact that this group, SL2 of C, is a double cover of PSL2 of C, which is the isometry group of the hyperbolic 3 space preserving orientation. Inside of SL2 of C, it will be interesting to think that we have also the real form of the group, which is a double cover of PSL2 of R, which is the isometry group preserving orientation of a totally geodesic plane into the 3 hyperbolic space. Moreover, it's interesting also to have in mind that PSL2 of C acts not only on the hyperbolic 3 space, but on its natural boundary, which is a sphere. Imagine that the hyperbolic 3 space has the ball model. The sphere is acted on by PSL2 of C. The action extends in such a way that the action is conformal, meaning that this sphere has the structure of a complex manifold, which is the complex projective line, and PSL2 of C acts on the boundary of the 3 hyperbolic space as the conformal action by the Möbius group on the complex projective line. Inside of it, the real part of the group, the stabilizer of this totally geodesic plane, stabilizes also the real circle, which is the projective real line. Meaning that inside of it, PSL2 of R will act preserving this real circle, which is the projective real line, and it preserves the upper half space, upper half sphere, which is the Poincaré model for the total for the hyperbolic plane, and the lower half sphere is another Poincaré model for the hyperbolic two-plane. So this is something we can have in mind. And with this group action, we see that PSL2 of C, quotient by the stabilizer of a point, would be exactly the hyperbolic three space, meaning that PSL2 of C over the hyperbolic three space, meaning the canonical projection of PSL2 of C on the quotient, it's a bundle, an SU2 bundle over the hyperbolic three space. It's the frame bundle of the hyperbolic three space. The action of the isometry group is free and transitive on the bundle of orthonormal frames of the hyperbolic three space. In such a way, if you have gamma, a uniform lattice in the isometry group of H3, meaning a uniform lattice in PSL2 of C, the quotient of PSL2 of C over gamma is in fact a six-dimensional manifold, which is the frame bundle over the quotient of H3 over gamma, meaning that this quotient of the hyperbolic three manifold by this uniform lattice, it's a compact three-dimensional manifold with a hyperbolic structure in the Riemannian sense, and its orthonormal frame, it's a six-dimensional manifold with the structure of a quotient of PSL2 of C by the fundamental group of the three hyperbolic manifolds. Yeah. It's two, PSL2 of C. PSL2 of C is the frame bundle of the hyperbolic three space. Yeah, also for the quotient. The quotient of PSL2 of C over gamma is the frame bundle of the quotient of H3 by gamma. This is a compact hyperbolic three manifold. Yeah. There is kind of converse construction of this. If you have a three-dimensional manifold, real manifold, with a Riemannian metric, this frame bundle of the manifold has a tangent space, which is isomorphic with the fiber in a point is the orthogonal group plus R3. The R3 is the horizontal part, and SO3 is the vertical part. They are isomorphic since for a vector in R3, you can associate the skew product with the vector seen as an element in the Lie algebra of the orthogonal group. So this defines a complex structure in the tangent bundle in the frame bundle of any three-dimensional Riemannian manifold. And what I'm saying is there is a theorem. This complex structure is integrable if and only if the curvature of the Riemannian metric is constant equal -1. So those three-dimensional hyperbolic manifolds have this property that they admit an almost complex structure on the orthonormal frame bundle, which is integrable. And in fact, it's a quotient of SL2 of C. So now I will give some explanation about the geometry of those quotients of SL2 of C. First explanation is all those manifolds do not have inside hypersurfaces. If you take some complex semi-sample Lie group, you take a compact quotient, These results say that there is no compact analytic subset of complex codimension 1. There are no hypersurfaces. And this result go into the direction to say that there are no meromorphic functions. Since if on some complex manifold, you admit meromorphic functions which are non-constant, the level sets of these meromorphic functions will give you like a singular foliation. And it will give you infinitely many compact analytic hypersurfaces of codimension 1. So proving there are no hypersurfaces proves that those quotients are far from being algebraic. They have algebraic dimension 0. They don't have any non-constant meromorphic function. So we are far from being Keller, far from being algebraic. It's something about non-Keller manifold, compact non-Keller manifold. Moreover, we are in a situation where this theorem of Raghunathan does not apply. Raghunathan theorems say that in general, for the quotient of a complex semi-simple Lie group, if there is no local factor isomorphic to SL2 of C, the Kuranishi space is trivial. This manifold is rigid. There is some case which was let aside by Raghunathan vanishing theorem, the case of SL2 of C. And this rigidity or flexibility about the manifold quotient SL2 of C by a lattice was solved by Gis in a paper where he constructs non-trivial deformation of the quotient SL2 of C over gamma. Those non-trivial deformations are constructed in a geometric way. They use some locally homogeneous geometric structure for which I will give you the definition. So the context is what we call a GX structure on a manifold. That means that we have a manifold in such a way that the manifold is covered by open sets. Each open set admits a chart with values in some homogeneous space. Moreover, on the overlap of such two open sets, the transition maps on the intersection are defined as being the restriction of an element in the group. This means exactly that this element is locally constant. This means exactly that defining a GX structure defines a flat G bundle on the manifold. In fact, here the model G over H has the same dimension as the manifold M, and you have transition maps which are such that given by elements in the asymmetry group G. This definition is exactly what you need if you want to endow the geometry of the homogeneous space on the compact manifold. You want everything which is true and G invariant on the homogeneous space will have some intrinsic meaning on the manifold having a GX structure. And now here you have two things. You have this monodromy map, which is the monodromy of the flat bundle associated to these transition maps. This flat bundle becomes trivial on the universal cover. It becomes a trivialization, it becomes a product of the universal cover times the group G. And on the universal cover, this geometry, if you pull back the GX geometry on the universal cover, what you get a map from the universal cover into G over H. This can be seen also as a reduction of the structural group of this G bundle to H. So basically those GX geometries on simply connected manifolds are given just by local diffeomorphism. On the manifold M, you don't have a map, but you have the fact that this developing map is equivariant when the fundamental group acts on the universal cover of M, and it acts on the model X through this monodromy representation. So this is classical description of what we call a GX structure on a manifold. So let me say also that there is some extra feature which appears when the manifold G over H is Riemannian. In the case where the G action on G over H preserves some Riemannian metric, which is exactly the same as saying that the group H is compact. In this case, the classical Hopf-Rinow theorem about geodesics on Riemannian manifolds on compact manifolds, completeness of geodesic, will imply that, in fact, this developing map must be a global diffeomorphism. This will imply, in fact, that your universal cover identifies with the model. It's a cover of the model, but if the model is simply connected, like here, you will have an identification of the universal cover with the model, and your manifold is a quotient of the model by a discrete subgroup in the symmetry group G, which is isomorphic to the fundamental group of the manifold. In general, here, we will not work in the case where H is compact, because I will work in the framework of complex manifolds. In the framework of complex manifolds, I would like that G be a complexly group, like SL2 of C. H will be a subgroup in it, in such a way that G over H is a complex manifold acted on holomorphically by G. This means that the manifold M will inherit some complex structure coming from the complex structure of the model. So there will be some compatibility in the complex structure of the manifold and the complex structure given by the GX structure. And in this case, the completeness theorem is not always true. I will give you some classical example of GX geometry on a manifold. The classical example appeared on Riemann surfaces when people studied linear differential equations in the complex domain. This object, like this kind of Riccati equation, is something which is very usual in the complex analysis, is a linear second order differential equation. We know that locally, the space of solution is a two-dimensional vector space, meaning that if you have a basis of solutions and you go around a closed curve and you come back with a twist, which is a linear map. So this base of solution changed by a linear transformation. When you take locally the quotient of two solutions, this twist will be a homography. It will change your base of if V1 and V2 is the local base of solution. When going around a path, you will come back with some twist, which is something like this. You will come back with something which does not take the same value, but it becomes something like A plus BV with A, B, C, D, complex numbers, an element of PSL2 of C, uniquely associated to an element in the fundamental group. This is exactly what we call a GX structure, where the model is the complex projective line and the symmetry group is PSL2 of C. So a Riemann surface endowed with some linear differential equation will have this kind of complex projective structure. And in fact, this was exactly one of the proofs given by Poincaré for the uniformization theorem for Riemann surfaces. In the case of compact Riemann surfaces of genus G greater than 2, this is exactly what he did. He just first was able to find a complex projective structure compatible with the complex structure of the Riemann surface. This is a first work. And the second point is to find among all complex projective structure, one with very nice developing map. You will find one with real monodromy. The real monodromy will preserve the upper half plane, and the developing map will give an isomorphism between the universal cover of the surface and the hyperbolic two-plane. At the end of his proof, the Riemann surface is uniformized in the sense that it is a quotient of the upper half plane by a discrete subgroup in PSL2 of R. Those kind of groups are called Fuchsian. Discrete subgroups in PSL2 of R with compact quotients are what we call Fuchsian groups. The name was given by Poincaré. Now let me give, sorry. Yeah, so in general, W will be a local biholomorphism from the universal cover into some open set in the complex projective line. So the developing map will give you, in general, some map from the universal cover of the manifold into P1 of C. Now you will want to ask that the monodromy morphism stay in PSL2 of R in such a way that you will stabilize open sets in the complex projective lines. You will stabilize the upper half plane. But there is some work here because there are many complex projective structures. And at the end, there is only one which realizes an isomorphism between the universal cover and the upper half plane. And the good tool which Poincaré used without having it completely was this kind of deformation of the GX structure, deformation of the complex projective structure. What is written here is that you have this space of all complex projective structure on the Riemann surface. And at each complex projective structure, you have a group homomorphism going from the fundamental group of the surface into PSL2 of C. And the theorem proved first by Ehresmann, then by Thurston, is in fact, those two spaces are locally homeomorphic. This character variety, this quotient, is the quotient of G acting on itself by post-composition, post-inner composition. So in fact, if I have a group homomorphism, which comes from a geometric structure, and I deform it a little bit, it gives me another GX structure close to the initial one. It's kind of geometrization of group homomorphism, which stand near the geometric homomorphism. And this very general principle can be, for example, applied to obtain the first result about the rigidity of lattices inside Lie groups. There is a very long story about rigidity of lattices, but one of the first results proved by Weil is very general. Here you don't have assumption about the rank of the group, about no compact factor, no SL2R factor. It's something very general, which says something weaker than the usual results of rigidity. It says that if you take a lattice in a group and you move it a little bit, it stays discrete, and there is no, it stays injective. There is no kernel. Of course, there are more involved results of rigidity. This is a local result. And there is a stronger result by Weil and Zellberg saying that if the group G is not locally isomorphic with some SL2, there is no SL2 factor, there is no compact factor, then in fact the two lattices are conjugated by an inner conjugacy inside G. But, sorry. Yeah, so here, for example, if you look to this character variety, the topology of the group homomorphism from the fundamental group into G, you can see it like this. It's an algebraic set because the fundamental group of a compact manifold is a finite presentation. You have a finite number of generators. So to each element, you associate an element in G. So it's something inside G times G times G. But then you need to take quotient by relations. Relations are algebraic relations in the group. For example, in the fundamental group of a Riemann surface, what you have is the fact that here you will have a fundamental group will be given by generators, and the product of the generators is 1. So in fact, you will have 2 G matrices and a relation. So it will be 6G minus 3 parameters. When you take the quotient by inner conjugacy, it's 6G minus 6. It's a manifold of dimension 6G minus 6. There could be singularities. You can take here a quotient in the sense of geometric invariant theory, that there could be some singularities. If you take irreducible representation, this open set is smooth. Okay. So this kind of result can be obtained through Ehresmann-Thurston principle, just thinking about the fact that if you take a quotient of G over gamma, and you think of it as a manifold, think about the fact that G could be simply connected as for SL2 of C, then G will be the universal cover of the manifold N, gamma will be the fundamental group. Now the monodromy morphism of this geometric structure seen as a GG manifold, where G is the symmetry group acting on itself by translation. The monodromy morphism will be something going from the fundamental group of M into G. And in fact, it will be this embedding of gamma into G. So moving a little bit the morphism by Ehresmann-Thurston's principle, say that you move the GG structure. But it's a Riemannian structure since H is identity. There is some Riemannian metric which is G invariant on G. So it's a complete manifold. So it will be another quotient of G by another way of putting the fundamental group into G. This gives a theorem. Rho gamma and gamma are 2 isomorphic groups because they are, both of them, the fundamental group of M. And this also was used by Etienne Gis when computing the Kuranishi space of the quotient of SL2 of C over gamma. Sorry. Yeah, this is what I said. What I said is that this GX structure think of a translation structure. For example, if you have a holomorphic one form, on the open set where the holomorphic form does not vanish, you are identified with C, but up to a translation. This is a GG structure where G is the group C acting on itself by translation, meaning that you have some coordinates in a Lie group which are well defined up to translation in a group. This is exactly what happens when you take integration of a differential form. You have a primitive. The primitive is the developing map. It's well defined up to a translation. Yeah. What I said is that by the definition of this GX structure, if you take local trivialization, the transition mapping between those two trivialization sets is given by a unique element in G. Unique element in G. So when the intersection is constrained, it's rigid. Yeah, so this is your G bundle. You are right, you are right. In fact, what is important here is that locally, your manifold is diffeomorphic to G over H. Oh, you're right, you're right. In fact, in the name X, you need to think about it as G over H. So what is inside G over GX is a space with a symmetry group which acts transitively. And if you give the action, you will give the isotropy group H. You're right. And Gis in his theorem start with this SL2 of C over gamma. First of all, if you want to move, so here G is SL2. If you want to move SL2 of C, gamma into SL2 of C, you are not able. Most of theorem of rigidity will say that for uniform lattice in SL2 of C, if you put in two different ways the uniform lattice into SL2, the two different ways are the same up to inner conjugacy into SL2 of C. A geometric way to say the same is to say a hyperbolic 3 manifold is completely determined by its fundamental group. You take two hyperbolic 3 manifolds with the same abstract fundamental group, they are isometric, the same. So you are not able to put in a different way gamma into SL2. But what Gis observed is that, in fact, you can take a bigger group, like SL2C times SL2C, acting on itself by translation, by left and right translation. And here G will be SL2 times SL2, and H will be SL2 of C, which is diagonally embedded in SL2. So the action is by left and right translation. In fact, if you think that SL2 is the complexification of S3, the compact group S3, S3 with the round sphere, seen as quaternions of norm 1, it acts on itself by left and right translation, preserving the round sphere. So here in the complexification, the metric is the determinant of SL2 of C, and it acts on itself by left and right translation, preserving this holomorphic Riemannian metric, which is the determinant. And here you are able to put gamma first into SL2 times SL2, because for the standard model, SL2 of C over gamma, you just put gamma here. You put identity and gamma. On the right factor, by Mosto rigidity, you cannot do anything but inner conjugacy. But on the left factor, you can put something. For example, if the first Betti number of the group is strictly positive, that means that there exists morphism into C star. So we can put in one parameter subgroup in SL2 of C, and you move your SL2 times SL2 structure. And Gis theorem is exactly this. It says that, in fact, you can move in this SL2 times SL2, the GX structure, and you have this forgetful map, which associates to SL2 times SL2 structure, the complex structure endowed on the manifold. His proof shows that it is an isomorphism. So he proves first that it is the same to move into SL2 times SL2. Think about this deformation as being in a sub-pseudogroup of the pseudogroup of local biholomorphism. When we do deformation of a complex structure, we work with a pseudogroup, the pseudogroup of local biholomorphism by definition. Here, inside this pseudogroup, we put another one, those which are left and right translation on SL2. Gis said that, in fact, it's the same to take deformation in the pseudo group of left translation. There exist those deformation, and they are isomorphic with the deformation in the large of the complex structure. It's saying that the forgetful map is surjective. And this gives a corollary, which was also proved independently by Rajan. If the first Betti number is strictly positive, there are non-trivial deformations of SL2 of C over gamma. There exist non-trivial deformations. So those manifolds are flexible. And here, the Zariski tangent space of the Kuranishi space is described as being completely determined by the topology of the hyperbolic 3 manifold. In his paper, Gis asked the following question. Since we know that there are no hypersurfaces in SL2 of C over gamma, are there any curves? The question is, are there holomorphic maps from some Riemann surface into SL2 of C over gamma? Notice that those holomorphic maps, as I described the complex structure here, they are not vertical, they are not horizontal, they are diagonal in the frame bundle. It is asked about holomorphic maps for Riemann surfaces of genus G greater than 2, because it's not hard to find elliptic curves. In SL2 of C, you have many one-parameter groups, some of them parameterized by C star. If you put in the good direction, you will meet elements in the fundamental group gamma. So you will descend on a map, which is a quotient of C star by some non-trivial element. It will be an elliptic curve into SL2 of C over gamma. But the question of holomorphic curves of genus G greater than 2 seems to be more involved, and Gis had a strategy. He observed that this is completely equivalent with a statement about connections on the trivial group. He said, but in fact, it is exactly the same problem as the following. I have a trivial group. I have that assume on sigma. I have the trivial rank 2 holomorphic vector bundle for some complex structure. And I take the frame bundle of it, so the principal bundle associated to it. I put it on the universal cover. And imagine that on this bundle, I have some other connection, saying it's another connection. It's saying that it's irreducible. The trivial connection is not irreducible. I take an irreducible one, which happens to have, if monodromy gamma into SL2 as a co-compact group. This other connection, it's flat. It will give another trivialization on the universal cover. That it will give a difference between this trivialization and the other one. The difference will be a map from the universal cover into SL2 of C. This will descend on sigma, but I need to take the quotient by the monodromy mostly. This is the undeterminacy if I want to see this map directly defined on sigma. So in fact, if I want to realize, it's equivalent. If I want to realize an embedding of my Riemann surface into the quotient of SL2 of C by gamma, it's enough to be able to realize on sigma this gamma as the monodromy of some holomorphic connection on the trivial bundle. And in fact, he asked a more general question then, which would be, what are all the monodromies, all the flat bundles, which could be realized as holomorphic connection on the trivial bundle? You can think about it like this. Think about a topological object. This morphs from the fundamental group into SL2 of C. It's a flat bundle. A flat bundle makes a good meaning for any Riemann surface structure. So I have my flat bundle and I move above the Tate-Müller space. When I move up above the Tate-Müller space, the holomorphic bundle will take different incarnations. The question is, can become trivial for some complex structure in the Tate-Müller space? Is it possible for this representation? So what are the representations where the bundle becomes holomorphically trivial? There is some chances that that works, because if you look for parameters for representation of the fundamental group of the surface into SL2 of C, we have seen is 6G minus 6. The Tate-Müller space is dimension 3G minus 3. Now, if I have an element in the Tate-Müller space, so take couples like this, sigma and delta. Sigma is in the Tate-Müller space of X. So this is 3G minus 3 parameters. Delta is a connection on the trivial bundle over sigma. Means that delta is a section of the canonical bundle of sigma times SL2 of C. This is 3 holomorphic forms over sigma. There are 3G of them. So here 3G minus 3. And minus 3 is linear gauge, linear changing of coordinates. So both structure here has 6G minus 6 parameters. The first result goes into this direction. It's a local result. It's about saying Derwan, Calzamiglia, Heu, and Loré, they proved that in fact, the monodromy map between this space of what I call systems, meaning pairs of a holomorphic structure on the topological surface and a holomorphic connection on the trivial bundle, this space of system, you could think about irreducible connections. It becomes smooth. And you have the monodromy map into the character variety. They show that this map is a local biolomorphism, meaning that in fact, you can move if you are able to find an element realized on the trivial bundle, you move a little bit the flat bundle, it will be also realized. It's a local result, which we were able with Indranil to generalize in higher genus for the surface. And we also did it for groups of any dimension, complex affine groups of any dimension. So in dimension 3, since the manifolds have the same dimension, and we show that it is an immersion at the generic point, this will show that in fact it is a local biolomorphism at the generic point. And generic point is important. We need to get rid of hyperelliptic structures on the surface and also to some connections. In fact, it's a transversality result here that we prove. In fact, the point is if you forget about the trivial bundle here and you look to all connection on all holomorphic bundles, the fiber over a flat bundle is what we call the isomonodromic foliation. So the result is a transversality result between the isomonodromic foliation, which is the kernel of this map, and the submanifold of systems where the bundle is trivial. And this transversality result, after some work, becomes equivalent with the following statement. You have W, a linear space into the canonical bundle of some Riemann surface. And for generic W, of dimension 3 and sigma not hyperelliptic, the multiplication map going from W to the section of W squared is surjective. This is proved in a paper of Giesecker, and the proof is attributed to Lazarsfeld. So this transversality condition is exactly this. Think that this W of dimension 3 is generic, so the connection must be generic, and the Riemann surface must not be hyperelliptic. Now, after this local result, there are still questions about how to realize co-compact, how to realize precise monodromies. For example, this question was asked by Bers, it's reported by Katz, the following question: try to characterize algebraically all holomorphic vector bundles of rank 2 over Riemann surfaces such that the monodromy is real, or such the monodromy is real and discrete, what we call Fuchsian monodromy. Of course, this is inspired by Narasimhan-Seshadri result, which gives completely the answer for the compact group. If you have a representation, a fundamental, a flat unitary connection on a bundle, this bundle must be polystable. So if the representation is irreducible, the bundle must be stable and of course of degree 0. So Narasimhan-Seshadri completely gives the answer for the compact group, but not for SL2 of R, for example. Also, this is a remark, if you work with what we call complex projective structures, we have seen that complex projective structures are used to uniformize Riemann surfaces. When you look to complex projective structure as linear differential equations, those are connections of a rank 2 bundle over the Riemann surface. The bundle here is completely determined. It's the following bundle called Gunning bundle. You have the canonical bundle of the manifold, and lifting a morphism from the fundamental group of the manifold into PSL2 of C, lifting it to SL2 of C, this is always possible for a complex projective structure, and this determines what we call a square root of the canonical bundle. This determines a theta characteristic. There are 2 to the power 2g of ways of lifting from PSL2 of C to SL2 of C, because there are 2 choices for each generator, and all of them will satisfy the product of the commutators make 1. So now the Gunning bundle is the following. You have the theta characteristic inside the canonical bundle, and this extension, all extensions are parametrized by C. You take the one which is non-trivial, the one which is determined by 1. So this is the unique Gunning bundle on which you realize all complex projective structures over a compatible structure of Riemann surface. For example, this is the case for the uniformization. If you take the uniformization bundle, it takes values in SL2 of R, and the bundle is the Gunning bundle. But of course, if you change the complex structure of the base, the bundle becomes different. It's another bundle. And this is the sense of the question of Nicholas Katz and Lippmann-Bers. So we worked in this direction, and our first result, this exact sequence means that no, sorry, this is not the canonical bundle. This is the bundle, or rank 2, sorry. This was the rank 2 bundle on which the connection is defined. This rank 2 bundle has inside a holomorphic line bundle, which is of degree G-1. So you have a map from L into V. The square is the canonical. So the extensions here are parameterized by the morphism from L-1 into L, H1 of L-1 into L, which is H1 of L2, which is H1 of the square of the canonical bundle. And then this is isomorphic by Serre duality with C. So there are extensions which are trivial, but I take the one which is not trivial, which is associated to 1. Are there other questions about this? Yeah, sorry, I was wrong. It's the rank 2 bundle, which is the square of the canonical bundle. So our result is the fact that we can realize some Fuchsian monodromy representation on the trivial bundle over a very symmetric hyperelliptic Riemann surface, which I will describe. And we can describe infinitely many connections which have this given Fuchsian monodromy representation. Together with the result of Calzamiglia, Derouin, and Loret, we know that if we are able to realize this given Fuchsian representation, we can take perturbation of the monodromy morphism into SL2 near this Fuchsian representation and cover by our connection of holomorphic bundles a neighborhood in the space of what we call quasi-Fuchsian representation. So neighborhood into SL2 of the representation into SL2 of C. So we are able to cover with connections on some other Riemann surfaces of genus 2 on a neighborhood in the space of quasi-Fuchsian representations. Those quasi-Fuchsian representations are associated to some quotients of the hyperbolic 3 space, but which are not compact. They can be compactified, but they are not compact. So we get some curves with G's principle, but not into the compact quotient of SL2, but in some nice quotients of SL2C, which can be compactified. So this is the first result. And the second result is changing a little bit the method. We were able to realize also some other Fuchsian representation, which happens to lie inside of a co-compact lattice in SL2 of C, which is associated with a tessellation of the hyperbolic 3 space by dodecaedron. There are some symbols here, 5, 3, 4. The 5 means that the dodecaedron has faces which are pentagons, 5. And there is a tessellation of the hyperbolic plane by pentagons. And this tessellation can be extended to the 3 hyperbolic spaces to a tessellation by dodecaedra, where 3 means that on a fundamental cell, on a dodecaedra, there are 3 pentagons around a vertex. And in the 3-dimensional space, there are 4 of them around an edge, meaning that the diedral angle is P over 2 in the hyperbolic 3 space. So now I will try to give a hint of how things works to find those. I will say the following. First of all, we limited ourselves to some, let me say, we limited to some hyperelliptic surfaces which satisfy those equations. So basically, another way to say it is that we work with a family of Riemann surfaces of genus G. So we are genus G. And we assume that there is an action of Z over G plus 1 with 4 fixed points of order G plus 1, meaning exactly that this will have a map from the Riemann surface into the complex projective line, which is ramified over 4 points in the projective line. This family is one complex dimensional family. It's parameterized by the cross ratio of the 4 points. So it's a one complex parameter family. Now, inside, I will look to a one parameter real family where the cross ratio is real. This means that I can choose those 4 points to be rectangular, as in this equation. So I have one line, one parameter family of hyperelliptic Riemann surfaces. It's hyperelliptic because I will consider those. I will consider those which have a real structure. So those which are like this have a real structure, which is the involution symmetric with respect to the diagonal. So there is some real structure. And I look to those symmetric Riemann surfaces, which are preserved by this involution. So it's a one parameter family. They are hyperelliptic because this involution will have 2G plus 2 fixed points. So it's a characterization of yeah. Sorry? The involution here is the symmetry with respect to the diagonal. No, I consider them now. I consider now those inside the family of hyperelliptic surfaces, inside the family of those which admit this. I consider those which are invariant by a real involution. And this will imply that it's a one parameter family, real one parameter family. Probably I said it in the wrong way. First, you consider those which are invariant by this action, gives one complex family. And now you consider those which have this extra real structure. It's a real one submanifold. And on those, I look to those connections which are also invariant by these involutions. And I will describe them as connections on the 4-punctured sphere. So those connections on the first punctured sphere, if I consider those which are real and eta invariant on the 4-punctured sphere, also I consider that the local monodromies are the same around the 4 points. And I consider that the local monodromy is compatible with the fact that when I pull back the connection to these compact Riemann surfaces, there is no local monodromy anymore. So I consider that the local monodromy has a rotation angle, which is 2p over k plus 1. There is some fixed local monodromy here in such a way that when I pull back on the smooth surface, there is no local monodromy anymore. And now with this fixed 4 local monodromies, my character variety is characterized by 3 coordinates, which are x, y, and z, given here. But they are related by an equation, which is a well-known equation in the character variety for the sphere. So it's real dimension 2. With the extra symmetry, which is here, which is exactly the thing that we are eta invariant, they become of dimension 1. So those are 4 connected components of dimension 1. And one of them, they are given by those inegalities. I took one where the traces are all less than -2. Here, the traces are all more than 2. There are inequalities which describe the 4 connected components. Now, what I'm saying is that the Fuchsian representation, which is the uniformization of the orbifold here with this 2 pi minus k angle. Yeah, k is what is needed when you pull back g plus 1. Yeah. So this Fuchsian representation is here. And we also look, when you pull back this representation to the compact Riemann surface, it becomes Fuchsian. But you want to say that, let me put things like this, Fuchsian representations are characterized by the fact that they are real and they have maximal Euler class. It's a connected component in the space of real representations. The connected component with maximum Euler class. So what I want to find is some connection on the trivial bundle, which has real monodromy and maximum Euler class. In order to know that I'm a maximum Euler class, it's enough to know that I'm in the same connected component that any Fuchsian monodrome. So when I pull back this one, what I want is to know that in the same connected component on the 4 punctured sphere, there is another connection which has the property that it is realized on the trivial bundle, on the holomorphic trivial bundle. And since here we are on the 4 punctured sphere, we look we realized the Ram connection on our compact surface as a logarithmic connection on a 4 puncture sphere. As a logarithmic connection, there is some data, a parabolic data at the puncture and the Higgs field. So we look in the direction of this Higgs field in order to realize a real representation, which will be exactly in the same connected component. So when we pull back on the compact Riemann surface, we are in the same connected component and we have real monodrome. And we are realized on the tangent bundle. So this is, roughly speaking, the part. And at the end, the idea is to we realize all the connected component here with traces less than -2. We realize them, all the connected component as holomorphic connections on the trivial tangent bundle. And then we are able to put one of them inside the co-compact Fuchsian lattice, which is the one that I described. So basically, we are inspired by those questions of Gis, bears, and cats. And we solve a very tiny part of it because we are able to realize some given connections on the trivial bundle. But of course, this very nice question of cats is widely open to algebraically understand those bundles, those holomorphic bundles, which admit connection with real monodromy and with Fuchsian monodromy. I will stop here.
Questions?
Yeah, so on the real manifold, they are very closely related with constant mean curvature equal 1 surfaces in the hyperbolic free space. There is a nice work of Gianpietro Pirola about CMC1 surfaces in the 3 hyperbolic space. And in his work, they are given by a flat unitary connection plus a nilpotent Higgs field. And in our work, our Higgs field, which we use, it's never nilpotent. So I do not know exactly how to relate the work of CMC1 surfaces in H3 with our construction. Because as we did the construction, we never have this Higgs field to be nilpotent.